All right, this next section is one you're really going to need. We talked about for the motors and so forth. We're going to talk now about primarily EMIOS. Just a quick one slide on Watchdog and PIT. They're pretty simple. But the EMIOS is, it stands for the Enhanced Modular I/O System, but it's basically your timed inputs and outputs. And there will be a number of channels, dozens of channels. Each channel has a pin, and you can specify, are you a PWM? Are you an input capture? Are you a one-shot output, etc.? So we're going to go through that, and then we've got another exercise. First of all, the Watchdog. The Watchdog after reset is turned on. So you can either service it on a regular basis by following these instructions here, or disable it as in all the example code. Okay. There's also window modes you can use if you want to make it more secure. There's locking, unlocking involved also. But just enough said on Watchdog. You've all probably used one before. The PIT, you've probably all used a PIT before, and everyone uses the same name, but my control might be different. The PIT is clocked by system clock, so it counts at 64 megahertz. It's a 32-bit counter, so it counts a long time. And each PIT has its own counter, so they're all independent of each other. And every PIT can generate its own unique interrupt request. And some of the PITs can be used, instead of an interrupt request, to generate a DMA request. And we're going to talk about DMA later, but let me just give you a little teaser on DMA, which is direct memory access. DMA is simple. You know, normally a peripheral flag asserts for an interrupt request. It says, hey, I want an interrupt, and the CPU, when it gets to it, it's enabled, says, okay, what do you want? And the CPU saves registers and then does something, and then restores registers and goes back to what it's doing. On a DMA request, peripheral asserts its flag, and if you select a DMA instead of selecting interrupt, then a transfer is done from A to D of whatever you've specified or previously described. We'll have certain number of DMA channels, and each channel you will configure to describe what you're transferring from a source to a destination, how much, and how does it do it, etc. And then you have options, after doing that so many times, generate another interrupt request. So there's no CPU involved in a DMA request, and that's a nice thing about it. So you can avoid interrupts by using DMA. So the PITs can do this, generate a DMA request after a timeout. And there's a third thing a PIT can do. Some of the PIT channels can be used to trigger an A to D. And there are two different ways here, but just for now, just know that you can trigger an A to D off of the PIT. When we get to the interrupt example, we'll use the PIT. Any questions on it? Okay, EMIOS. The EMIOS consists of dozens of channels for dozens of pins, depending on which device you get from us. And each channel can run in a number of modes for it to be a timed I/O function, input or output. So these are what the EMIOS channel mode choices are. Now caution, not every channel can do all of these. That's coming up. But these are what's on the Bolero product. You can be a counter, and the abbreviation is MCB. That's our modulus counter. It can be an up counter or up down. And then for inputs, we can have a single action input compare. This records what time did a transition occur on the input. If there's one action, in other words, a rising or falling edge, and I can specify, or either one, what time did it occur? So here if a counter is involved, and I can specify what counter I want to use. So, you know, whose watch? Hey, the door opened. Oh, what time did that happen? Use my watch, or use Josh's watch, or Lydia's watch, someone else. You select a counter. And then input pulse width measurement, I can detect two edges. So I can either detect the same edges for a pulse width, or for period, or different edges for a pulse width. And after the second edge is detected, then a flag goes off, which can be an interrupt or a DMA. And then software must read the 2 times and subtract the difference to get the pulse width or the period. Okay? We just record the times. It's done by hardware, you set it up. For outputs, I can specify when this counter reaches this value, make this pin go high or low or toggle, whatever you want. Okay? That's single action output compare. I can do for 2 edges though, and generate like a one-shot high and low pulse if I want. And then the rest are PWMs, output PWMs. So the normal PWM is in what is in the exercise is there's a common time base. And so you can have a simple example is an engine, okay? The engine will, every cylinder in an engine will have a spark plug that needs a pulse. It will have a fuel injector that needs a pulse, exhaust that needs a pulse. So, and these all occur at different times for each cylinder, but they're all referenced off the crankshaft, like so many degrees. So if you have one common, like a degree counter, that you can say at 5 degrees, cylinder 1 spark goes on, at 2 more degrees later, turn it off. At 16 degrees, exhaust on cylinder X, and then off 2 degrees later, that kind of stuff. So that's the advantage of having a common time base is you can synchronize output pulses, and that's the OPWM. The OPWMT is a special mode for a trigger that we'll see when we get to the ADD. It enables you to drive, for example, a solenoid, and you know what happens to solenoid current when you, or voltage, when you turn on that current. You get overshoot, and you want to really measure the voltage of the solenoid while it's being driven, so you want to delay a little while it's still on. So that's the trigger. It's a third time that you write for the PWMTs. The next one is pulse width and frequency modulation. Here you can specify the frequency, like it's 2 kilohertz, and then the pulse width, which gives you a duty cycle. And you can change, you can double the frequency and change them independently. The last one is center aligned PWM with dead time. So basically every time your counter reaches, let's say, a value of 100, you can turn on or off current to a motor, but you can also have, when it gets to 100, you can have a dead time, either going up or going down, to allow for, like, for an H bridge. Okay, we'll look at a few of those that I think you'll need later, but once again, not every EMIOS channel has all of the functions. And what you see here is there are 2 EMIOS modules, A and B, or we also call them 0 and 1. We have a sense of humor on that. And they'll be in a group that has certain functions available. So you have to look up in the manual for that channel. Now, all these timed I/O functions need a time base, or need a counter, right? For an input, you want to record when it happened. An output, you got to schedule it. So the clock for this comes from, in general, starts with the system clock, and which can be divided if you want. And then you have a global prescaler for each EMIOS. So the system clock, let's say it's coming in at 64 megahertz. You can divide it for all the channels by 64, and so now you have a 1 megahertz clock rate coming in, incrementing counters, for example. And maybe the other one you don't divide, you count at 64 megahertz rate.